The diagram shows a water wave in a ripple tank being refracted at the boundary between the region P and region Q. How does the wave in region P compare with the wave in region Q? Now, this seems like a very challenging question, but let me ask you this. If there is a glass surface, right? This is glass right here, and on the outside it's vacuum or air, doesn't matter. And this beam of light that hits it, and what do you think is going to happen to it? What do you think is going to happen to it right now? The angle of incidence, let's say, is 50 degrees. It's going to bend inwards, right? That's what you've seen from a less dense medium to a more dense medium. It's going to bend inwards and the angle is going to be less, right? So what's happening to the speed of light? Here it's almost as fast as vacuum, and in glass it's a little bit slower. Actually, they also teach that it's because of the change in speed that kind of slows down and kind of bends towards it. That's what's actually happening. Okay, so this is the same difference. You have air over here because these two have different depths. What's happening is this medium water is traveling differently than how it is over here. And if I would plot water waves how I'm, plotting light waves like just a ray diagram or just a straight line, take a look. Water enters like that and is exiting like that. I'm just matching the arrows, trying my best to. Like that. And and if this was the glass surface, if this was horizontal, it would be a little more clear that this water, water is bending inwards. This angle is much larger than the refracted angle. So this is the bottom side definitely is acting as the glass, so to speak, in our comparison over here, and this is acting as air. So what do you think? Is light more faster over here or over here? Faster here, slower here. Same comparison. So water is going to be faster over here, slower over here. How does a wave in region P compare with the wave in region Q? So the wavelength you can clearly see for P, this is P, this is Q. In P, the wavelength is actually larger. But the speed of the wave, what do you think? Is also faster. Oops. Correct answer is A. The graph shows the height of the water wave varies with distance along the wave, right? This is the height, sure, whatever. The graph shows the wave with which graph shows the wave with twice the amplitude, half the frequency, and the same speed? So twice the amplitude, this peak is currently at 4, so the peak should be at 8, but half the frequency at the same speed. So you don't really see frequency over here because it's not a time, it's not time over here, right? This is a real physical wave, but you can see the wavelength. So let's calculate the wavelength over here, or actually the speed. You can see the wavelength. Let's figure out the speed. Okay. V over here is equal to F lambda. Isn't that the case? So V is unknown. Our frequency is still unknown, right? And lambda is 8. So V equals to 8F. That's the velocity of this wave. So in our new wave, same equation. I don't get confused too much because I'm going to use the same variables again. The velocity needs to be the same, so it's going to be V, because the original velocity was V, right? frequency needs to be half. So the new frequency f, it needs to be half, right? And multiply that by the new wavelength, which I do not know, right? And the two variables over here, the frequency, because I don't know the original frequency, so I just used f as a placeholder. So I got velocity in terms of frequency, 8f. So can I replace this velocity with this original velocity because the speed remains the same? I'll put that in there. Put that in there. 8f, that's the v, right, is equal to half the frequency is lambda. Okay, f and f cancel out. 8 times 2 is lambda equals to 16. That's the correct way of doing it. 16, what is it? Centimeter. Okay, so the amplitude needs to be 16. That's one complete wavelength covering 16 meters, and the height is 8. I really enjoyed this question. Answer is D. What proves that a metal bar is a permanent magnet? It's gonna repel. Only a magnet can repel another magnet, right? Attracts, conducts, repels another end of magnet. The speed time graph represents a short journey. And what's happening is speed is 0, starts increasing, and it's getting higher and higher and higher. So the distance change over here per time is going to be, so there's like a, let's say the speed is 5 in the first 2 seconds. So distance is gradually increasing by 5. Now in the next pair of seconds, it's 10, right? So it's getting steeper. And we're being granular about it. We're not being continuous, so it's getting steeper and steeper. So you're gonna get a curve a lot like this if you smooth this out. Gonna shoot up. Let's see the other page. A looks a lot like what we just drew. That's our answer. Skydiver falls at terminal velocity. So he's free falling. He's falling as fast as humanly possible, right? He's falling like a rock. He then opens his parachute. Now he's going to start slowing down. Which row defines the direction of the resultant force on the skydiver and the direction of the acceleration on the skydiver immediately after he opens the parachute? So here's my skydiver. Here's my skydiver, right? And he's going pretty fast, and he's gonna, open his parachute. Right? And he does that, and he's gonna start slowing down. So what's his acceleration? He's actually decelerating, right? He's slowing down. So downwards he's decelerating, right? In other words, his acceleration is towards the top, right? So the direction of his acceleration is towards the top. So if his acceleration is towards the top and acceleration is proportional to force, and this is to the top, force has to be also towards the top as well, because net resultant force is net resultant acceleration. So upward, 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 upward. Answer is D. More in line with chemistry. During boiling and during melting, a substance either takes energy or gives out energy. Which row gives the energy transfer corresponding to the change? During boiling, they take energy, they get excited, they break the barriers set by atmospheric pressure, and they're released to the atmosphere. During melting, same thing, right? They're not moving because melting is solid to liquid. Solid, they're not moving. Now all of a sudden, they can move. What's changing? Their energy. So they took energy. Correct answer is D. A solid plastic cylinder is immersed in a liquid of refractive index 1.4. So it's 1.4. Here's some liquid, or here's some liquid, and this is just plastic, right? We don't know what. It could be air, it could be anything. Light travels in the plastic cylinder and strikes the inside of the surface at an angle of incidence of 70. The light undergoes total internal reflection. What are the values of the critical angle in the plastic and refractive index? So critical angle is, it's already past the critical angle. Okay, let's do a quite little revision. Here's my normal, right? Let's say if a light is incident at a point and tries to go through, it can either bend inwards or outwards, right? Depending on the different refractive indices of the two mediums, right? Over here, what's happening is the medium on the outside allows the light to refract away. So the refracted ray is actually, the angle is higher. So that's what's happening. So as you move this angle over here, let's say if you bring the light, shoot it through here, it's going to become lower and lower, right? Let's undo that. At one point, at a particular angle, once you start increasing the angle of incidence, at one point, this is going to flatline, right? And after that angle, any light will undergo total internal reflection, meaning it won't refract because it doesn't have anywhere to refract, and it'll start only reflecting. That angle is called the critical angle, right? So if it's undergoing total internal reflection at an angle of 70, it's already past the critical angle. Look at that, right? So if it's already past it, the critical angle is actually less than 70, right? It's less than 70. And over here, this medium, it's allowing the light to bend away, right? So when here's air, do you remember this example? Air in glass, right? And when a light, that's not a stream of light. That's still not a stream of light. When light hits the glass surface, it is refractive inwards because glass has a higher index, right? Higher index. And if it were to bend like that away, and if the refraction is higher, the angle is higher, that would mean the glass would have a lower index. So the index over here with the light is bending away is 1.4. So that means, I'm just comparing it to examples I know, right? I don't want to use too much logic. I'm just being smart about it. So this means this index over here for this material, whatever it is, definitely not air, it's actually larger than 1.4 because this light is acting as it's going from a less dense medium, denser medium to a less dense medium because it's being refracted away. So I'm going to highlight greater than 1.4. The correct answer is C. As sound waves travel from one medium to another, its wavelength increases. What happens to the frequency and the speed of the sound? So what happens to the frequency is frequency remains the same. So what's going to happen to the velocity if the frequency is the same, not changing, but lambda, what happened to lambda? This is increasing, right? So if this is getting larger, this also will be getting larger because this is the same, right? So speed will increase. Speed will increase and it's going to stay constant. The battery in a circuit contains two identical cells connected in parallel. Which row shows the relationship between current I1 and I2 and gives the electromotive force? I1 is entering over here, I2 is, think about it this way, if 100 electrons are flowing over here, they're not disappearing, right? So 100 electrons will flow out. So if 100 electrons are flowing in every second, 100 electrons are flowing out every second. So because it's the same wire, the current 1 is equal to the current 2, right? And current is what? Why do I talk about electrons? A current is just a flow rate of electrons. Flow rate of electrons. That's why I say 100 electrons per second, 100 electrons per second, right? Just as an example. It's not actually measured by electrons, it's actually measured by charge per second. So you don't count the electrons, you count the set of charges, and I think you have like 90,000 electrons giving 1 coulomb. So that's 1 coulomb per second. Okay, so this is equal. What about the electromotive force over here? They're in parallel. So this battery raises the electromotive force by 2, but over here it's also raising this by 2 from this place. It increases it by 2. Both are doing the same job in parallel, right? And it's kind of like they're trying to raise it. If they were on top of each other, they could have raised it by 4, but they're only raising it by 2. Sorry, 2, and it's equal. So the correct answer is C. Easy. The diagram shows a circuit of a hairdryer. That's the motor, 2 heaters. The fan has a power rating of 0.1 kilowatts. So this is 0.1 kW. And the heaters are at 0.4. This is at 0.4 kilowatts, right? The cost of electricity is 8 cents for every kilowatt hour, right? What is the cost of running for 2 hours when switch P is closed and Q is closed but R is left open? See, this is running for 2 hours. So the total power consumed, the total wattage for this machine, this hair dryer, is 0.5 kilowatts, right? So if this runs for 1 hour, if this is gonna run for 1 hour, right, it's gonna be 0.5 kilowatt hour. And if it runs for 2 hours, it's gonna be this value times 2, which is 1 kilowatt hour, right? The cost is 8 cents, 8 cents, right? Indeed, for every kilowatt. How many kilowatts are you using? 1. So this is going to cost you 8 cents. Correct answer is D. Why are the metal casings electrical appliances earthed? Because so they're not at a dangerous voltage, so you don't die if you touch them. Tell that to an iPhone. How many of you got electrocuted holding an iPhone while it's charging? Correct answer is B. A narrow beam of particles are fired. So they're very tiny particles. They're like literally, like very tiny particles. Very tiny. And they can go through atoms. And what is an atom really? An atom is mostly free space. It's about 99% free space. So what do you think most of the particles hitting a gold foil, which is made up of 99% free space, what's gonna happen to these beam of particles? It's just gonna go straight through. Correct answer is A. I'm going to cheat over here. The question says 2 blocks are joined together and one block has a density of 6 grams while the other one has a density of 9 grams. And what is the overall density? So it's going to be the average density, right? And if I take a closer look, if this is 1 centimeter, this is 1 block, they all have the same dimensions except for the length. So if I cut this block in half, it's not the neatest, like that, right? So that's 1 centimeter and that's 1 centimeter. So it's the same as adding 2 9 gram per centimeter cube clocks together, and this one is 6. So what's the average density of these? What's the average of these three numbers? 6 plus 9 plus 9, divide that by 3. I'm just going to make my life easier and just divide them first. So that's going to be 2 plus 3 plus 3, and the 3 is gone because I divided each number, right? So 3 plus 3 is 6, 7, 8. 8 is the average density. Cool, huh? The correct answer is C. A diver of weight 500 Newton stands at the end of a springboard that is 2 meters long and is fixed at point P. The springboard has a weight of 500 newtons. So if it has a weight, it's going to act through its center of mass, and it's going to point downwards at 500, right? And what's the weight of the guy? What's the weight of the guy? He's also 500. Wow. 500 as well, pointing down. And this weight, so to speak, is 1 meter away. So there are two moments being caused. The net moment is equal to, let's call it net moment, is equal to moment caused by the board, which is clockwise because it's going to point down, right? It's going to try to bend it that way, about P, right? So that's caused by the board, plus moment also is clockwise, caused by the, I'm going to call him a moron, right? That's also clockwise. So the moment given by is the weight of the object and its distance from the pivot, which is 1 meter times 500, right? Plus the moron is 2 meters away from the pivot times 500. That's 3 times 500, which is 1500 Newton meter. Correct answer is D. Correct answer is D. A tennis ball mass of 56 grams is traveling at 1500 meters per minute, right? So per minute, 1500, what is that per second? Oh my God. 1500 divided by 60 is 25 meters per second. 25 meters per second. Mass is 56, which is 0.056 kilograms. Standard units. Which expression equals to the kinetic energy? Kinetic energy is half mv squared. Half is half. Mass is, the mass is 0.056 and the speed is 25 squared. Oops. Minusing points for consistency. There we go. And what do we have? I think A is matching, right? Yeah, definitely A. Answer. Extremely large increase in pressure is needed to compress a liquid, so a lot of effort is required. A gas can be easily compressed much smaller with much smaller increase in pressure. Which statement will explain this? Molecules repel each other very strongly when they're close, kind of like opposite of magnets, if you, or like magnets if they're repelling. The closer you bring them, the more they repel. So same with molecules. The closer they get, liquids, they're very close. That's why they're kind of more or less stuck there. Matter liquids are generally considered incompressible, right? So they're so close, they're repelling each other a lot. Why don't they fly away? They don't have that energy, right? Energy, right? So A is the answer. Let's look at B, C, and D. The attractive forces between molecules are small at large distance. The molecules in the gas, well, that's actually true, I guess. But yeah, like no, not that it's not direct. Like you can say that's kind of because they're further away. Actually, this is a bogus point. Like people could think this is correct. I think this is more of an error point. You could say that actually, you know. Anyway, the molecules, like I wouldn't say it, but I wouldn't be surprised if someone selected B. Not too surprised. The molecules in the gas collide with the walls of the container and rebound. That's true, but what about liquids? They're the ones more difficult. Liquids do that too. The molecules of liquid are constantly moving. Okay, they're all moving at random except for solids. Correct answer is A.